Hello, my friends. We've got another spectacular physics problem. This time we've got a frog on a train. Crazy stuff, right? You never know when you'll need to be able to calculate this. All right. A frog is traveling on a flatbed train that is moving to the right at some speed. First things first, draw a picture. So we have our train moving this way with some velocity v naught equals 20 meters per second. At time t equals 0, the frog jumps toward the back of the train at an angle of 110 degrees. So that was meant to be 110 degrees from the front of the train. Okay, so this is the direction the frog is jumping with a speed of 5. So we want to write a couple of things here. So the first thing we want to write is the acceleration vector of the frog relative to the ground. Now, acceleration is kind of special. Um, the only way we can have acceleration is if we have some kind of force. Now, you haven't learned about forces yet, but in this case, the force is going to be gravity. All right? So there needs to be something pushing it. So this will just be the acceleration from gravity. That's negative 9.8. Everything, so the frog is in free fall at this point. Everything in free fall moves with this acceleration. Doesn't matter how fast you're moving. Doesn't matter um, if you're on a train. Doesn't matter. So that's our acceleration vector. The next part is we want the velocity vector with respect to the ground. So we want the velocity of the frog with respect to the ground. Following our little formula, we can use the train as an intermediary. So the velocity of the frog with respect to the ground equals the velocity of the frog with respect to the train plus the velocity of the train with respect to the ground. Velocity of the frog with respect to the train is 5 cosine of 110, 5 sine of 110. If you put your angles from the x-axis, this cosine, this sine with x and y will always work really nicely. And this is plus the velocity of the train with respect to the ground, which is 20, comma 0. So then we get 5 times the cosine of 110 plus 20 equals 18.3, comma 5 times the sine of 110, 4.7. Okay, so the frog kind of takes away a little of the train's velocity, but the frog is still effectively moving forward due to the giant velocity of the train. But the train is not at all in the y direction. And that's kind of what we see right here. So the only y motion you're going to get is going to be from that jumping of the frog. And then finally, we want the position vector of the frog. And if we say they start at the origin, so we'll say at t equals 0, y equals 0, and x equals 0. Okay? So we kind of have all the pieces right here. So the position of the frog with respect to the ground equals 18.3 times time. That's my velocity piece. And there's no acceleration in the x direction. So in the y direction, I'll get 4.7 t minus 9.8 t squared over 2. So now we have the position of the frog as a function of time while he's in the air. So what do I want to say? So remember, when you're doing these kind of vectorial kinematics, it's really just your regular kinematics equations, but this is in the x direction and this is in the y direction. So all I'm doing here is x equals x naught plus v naught t plus a acceleration in the x direction, t squared over 2. And this is the initial velocity in the x direction. And y equals y0 plus v naught in the y direction t plus ayt squared over 2. So that's really what this position vector is. It's just your kinematics equations, but in each respective direction. And if we were dealing in 3 dimensions, you'd have another one for z, and it would be pretty much what you expect. That's the answer.